record that. What we're going to be doing today is probably ruining my voice even more and going through a whole bunch of examples. So that's going to be the goal for today. Before we do that, though, and jump into that, I want to highlight a couple of things kind of coming up. So we have our second and I guess up until the final exam, our last exam on Tuesday. That's not this coming Tuesday, but like in a week and a half. So we have one more homework assignment that's before that we'll be due in a week, which is, it's just 3 problems. So it's not terribly long because I'm assuming you're going to be doing that and studying as well. The one thing to note on the homework assignment, some of that material will be covered on this next exam. So it's covering really the stuff that we've been doing the last week. So I wanted to make sure that that was on the exam. We didn't save all of that for the final. So because of that, for this next homework assignment, there won't be late submissions allowed because I'll release the solutions to that after class next week, Thursday. I have here, you can see kind of my study outline. So it's going to be a similar format to the last exam where there are maybe a couple of shorter problems and 2 longer problems. It's going to cover the stuff that we did since the last exam. So it could cover transient conduction, kind of like what we had our last quiz on, 2D conduction. Obviously, it's not going to be you're not going to have to make an Excel spreadsheet that can, calculate something, but it could ask for, say, maybe the equation for the temperature of a specific node, or you're given a temperature distribution and you have to calculate what is Q between these 2 points, or something with a numerical solution. There's you're given a bunch of temperatures at different places and asked what's the temperature of this node given the known values. So I would say, the main thing that you're going to need to know on that is kind of the end result of that, in class number 6, I think it was, where we went through and derived the different equations. You're not going to be deriving stuff, but you might need to know the end result. Then chapter 6 was where we looked at similarity. If we have this system, you get the Reynolds number and the Prandtl number to match, and then we can use that to calculate the Nusselt number and use that to find H. So be able to find, if we know everything about one system and we have a similar system, can you figure out what's the heat transfer in that similar system, or what's H in that similar system, or what conditions would you need? So it could be asking different questions about that, but all how do you take stuff in one setting and translate it to another setting? And then some stuff about external flow, which is what we've been doing, which is really looking at models like what we saw last class, where you have the Nusselt number is equal to some function of the Reynolds number and the Prandtl number. So it's kind of identifying what's the appropriate model and then being able to plug in the numbers and solve problems with that. So you get some practice doing that on this coming homework. But that, a lot of it is kind of identification and finding, what model applies. So as you might imagine, there will be a fairly hefty packet of reference stuff for you to use during the exam. I'm not 100% done putting that together, but I'll put that together and share that with you so that you have that so you know, okay, this is the kind of stuff that I'm going to be given. And I think that might help in kind of defining the scope as well. But that's in a week and a half. Let's maybe talk more about it next week, or you can, as you're thinking about it, you can ask questions next week. So last class, we looked at a system like this, where we had a flat plate and we knew the dimensions of this was 0.2 meters by 0.4 meters. And we had a gas flowing at T infinity of 25 C. At a velocity of 25 meters per second. And a pressure of 1 atmosphere. This had a surface temp of 230 degrees. And we calculated H for this problem if this gas was air. So with air, it was fairly straightforward. So the Reynolds number was 3.8 times 10 to the 5. Prandtl number was 0.690. And we used our model for average Nusselt number. We knew that it was laminar flow. Because of the Reynolds number, it was low enough that it was laminar everywhere. And this told us that the Nusselt number, the average Nusselt number, was equal to 0.644 Reynolds to the 1/2, Prandtl to the 1/3. And we actually saw at least a little bit that this was something that we could get from kind of first principles, this model. So we did that. We found what our Nusselt number was. Our average Nusselt number is then 350, which leads to a convection coefficient of 29.6. Okay, and this is typically kind of the solution process that you're actually going to use. Okay, look at the problem. What's the Reynolds number? What's the Prandtl number? Use those to identify what is the correct model. In this case, that was this model for the Nusselt number, and then find the Nusselt number, then use that to find H. So we'll do a new example. We'll call this example 2. So what if we change gases and our gas becomes carbon dioxide? Well, we're gonna do the same basic thing. We wanna, okay, first find the Reynolds number and the Prandtl number, and then figure out what's the correct model, and then use that to find the Nusselt number. So the Reynolds number at the end of the plate is U infinity L over nu, which is 25 meters per second times 0.4 meters divided by now the kinematic viscosity for carbon dioxide. So now we have to go up and look up some properties. Okay, so if we look at the properties, we have to figure out which temperature we want to look at. So typically for these problems, we're going to be looking at the average temperature in the system. So the average between our T infinity and our surface temp, because that's going to give us, right, all of these are temperature dependent. If you look at, we're looking at kinematic viscosity. It does change with temperature. So if we pick an average, that's going to have these kind of, even things out. It's going to be lower in some places, higher in others. We'll choose the average. So we did this before. The average temp is 400 Kelvin, which I chose some of the temps here to make that easy for myself. Okay, so we'll select out this whole row, and that's all of the properties that we need. We'll use this row. So our kinematic viscosity rate is 14.3, but we have to look again at what the units are. So this means that's 14.3. The times 10 to the 6 means this is times 10 to the negative 6 meters squared per second. Meaning if you multiplied it by 10 to the 6, then you'd get 14.3. Again, you just have to kind of get used to how the data is presented. Okay, so let's plug in that kinematic viscosity. The Reynolds number always has to be unitless, so you need to use units that will cancel each other out. This is 7.0 times 10 to the 5. Again, this is something that you have to look up. The critical Reynolds number for this specific flow is 5 times 10 to the 5. That means somewhere along the plate, we're going to be flipping from laminar flow below 510 to the 5. We're going to flip to turbulent flow at the end of the plate. So we have to find where on the plate that change happens, and then use two different models, one for the laminar region and one for the turbulent region. Okay, so we'll figure out where on the system that happens. So it's going to happen at some position X. We'll call that the critical distance. And this critical distance is 0.286 meters. So what we have on our plate there's 0.4 meters. We're going to have our boundary layer growing like this. And then all of a sudden it's going to go. So in this region, our flow is all laminar. And in this region, it's all turbulent. So we have this dividing line between the two, and we'll handle each separately. So how we'll do that is we can look at, just like we did before, this is going to be looking at kind of integrating, well, let's leave it like that for right now. Okay, so we already have a model for the laminar flow part. So we're going to be able to find the average convection coefficient in the laminar region. And then we need a new model for the turbulent flow. Okay. When we looked at doing this, finding the average convection coefficient over the whole thing, when we've done this before, we've looked at like integrating the convection coefficient over the surface. So we're going to be doing the same thing. So this tells us the same model. So the laminar convection coefficient, the laminar is 0.3. I guess this should be, I think, not 6. Let me double check what that number is. Okay, sorry, not 644, it should be 664. Because this is 0.332 times KF. Reynolds to the 1/2, Prandtl to the 1/3, X to the -1. This whole part. Scales as x to the minus 1/2. That's how the laminar boundary layer is growing. And if we remember watching that video of like the boundary layer growing as the flow is going over the plate, we said that, right, this boundary layer was proportional, ended up being proportional to x to the minus 1/2. And there was other stuff in there too, but it was growing as x to the minus 1/2. That's also how h scales. So if we're looking at turbulent flow, we want to look, how does the turbulent boundary layer grow? And h is going to scale similar to that. So for turbulent flow, we want our model we expect the Nusselt number to equal some function of Reynolds and Prandtl. Like C Reynolds to the M, Prandtl to the N, we expect it to look similar. And we expect H to scale kind of with boundary layer thickness. So they should be, like they were before, both scaling to the x to the minus 1/2. That should be similar. So for this, for a turbulent boundary layer, delta is proportional to x to the minus 4/5. Or sorry, not x to the minus, x to the 4/5. This should be not x to the minus 1/2, it's just x to the 1/2. Sorry. So the boundary layer scales as x to the 4/5, which means it grows a lot faster, kind of similar to how I drew it up here. And the laminar part, this thickness here, proportional to x to the 1/2. Here, you have x to the 4/5, right? X to the 1 would be just a straight line. So it's still a curve, but it's growing much faster. So we expect H to be kind of the same thing. And if we take data and fit data knowing these things, we can find so this scales similarly, which means that the Nusselt number at a specific location, which is hx times x over K. The new salt number should scale. So this is, this scales as 0.0296, so that's our constant, times the Reynolds to the 4/5 power, Prandtl to the 1/3 power. Okay, so we end up with a very similar equation. The boundary layer grows to the 1/2 in laminar flow, so the new salt number scales as Reynolds to the 1/2. Turbulent flow, the boundary layer grows as Reynolds as the 4/5 power. So we get new salt number times some constant Reynolds to the 4/5 power times Prandtl. So just to show these things are interrelated, it's not totally random what powers and stuff we end up with. This is just to describe what this equation is for. Right, so this assumes it's 2D, we have parallel flow, so the flow is in the same direction as the plate. And compressible. Constant properties, and this is kind of just to give a flavor. All of these models are going to be a little bit like this, where they all have specific cases where they work. And you have to identify, kind of like what we do in transient conduction, you're identifying what's happening in this system, and then looking and seeing, okay, what models are going to be describing what's happening in the system. So actually, like, choosing out the correct model is a lot of solving the problems. Okay. Just one other note. So in laminar flow, delta, the velocity boundary layer thickness, and delta T, the thermal boundary layer thickness, grow differently. So those are growing by both by diffusion. So this one is viscosity. This one is thermal diffusivity. For turbulent flow, both are growing because of mixing. So that's kind of the dominant factor. So they end up becoming essentially the same size, because the dominant factor is the actual mixing of the fluid, not diffusion, which is different because of different properties. So in turbulent flow, those end up both being related. Okay, so how do we actually solve this? Okay, so like what we did before, we know that the average H well, I guess this is, sorry. This is how we found average H before. So for this model, right, we're going to split that up into looking at the integral from 0 over the laminar portion. Plus the integral from where it turns turbulent to L. So we're basically going to add up the two different parts of this. Now, if you just look at the form of the equation, just a couple things to note. What you have to do is watch your bounds of integration, because we're integrating from not from like 0 to X. We're integrating like over that portion. And then, okay, again, if we go back to our picture, we want to integrate first over this part. And then we start here at XC to integrate over the last part. So we're like adding up H over all of those parts, and then dividing by the whole length, L, to get the average. Right, so you think that's what integration is doing, it's adding it up. So we add it up over the first part, then we stop, switch regions, add it up over the second part, and then divide by the whole business. So that's what we're doing. So this first part is adding up H over that whole laminar part. Then we stop, switch models, add up H over the whole turbulent part, then get the average by dividing everything by L. So if we do this, 1 over L, the integral from 0 to XC. Our model for the laminar part is 0.0332 times KF. Okay, and then we can add up the integral over the second part, 0.0296. One of the things to watch though, you have to watch out. Reynolds number has like a hidden X in it. So you have to make sure that that's right. We're integrating over X. Reynolds number has X in it. So it's not a constant. Okay, so we have to actually split that up. The write it like this, and handle. So this would be an x to the 1/2 times x to the -1. So this is x to the -1/2 dx. Messing up my bounds. 296 kf. And then this would have an x to the -1/5 dx. So then to figure this out, we have to just integrate. So when we do that integration, we can pull out a lot of the stuff. So this is both of these terms have kf in them, and both of them have Prandtl to the 1/3. So we can pull out kf over L. There's still going to be stuff over there. If we move this over to this side, that's just the Nusselt number. So we can look at that. That's going to be, we're going to still have Prandtl to the 1/3. And now we're going to have 0.332 times the integral from 0 to xc. So that's our first term. We are pulling out constants. Plus 0.0296. Okay. And then we have to do those two integrals. They're fairly straightforward, but they're kind of weird numbers. So for x to the -1/2, we would get 2x to the 1/2. For x to the -1/5, you would get 5/4 x to the 4/5. Is that right? So you would end up with the Nusselt number would be equal to 0.0296 664 times the Reynolds, the critical Reynolds number to the 1/2, preamble to the 1/3, right, where this is U infinity XC. So that's the same model as laminar flow, that's just the laminar part. And then we would get a turbulent part, which would be plus 0.037. And then this, because your bounds are from XC up to L, you would get both of those showing up here. Reynolds number L to the 4/5 minus that. So this is, again, if you want to look it up, kind of look at it at two different parts. This part is because of laminar. From 0 to XC. This part is because of turbulent from XC to L. So you get, in some ways, kind of like a correction. So if we think about it like this part of it, that is like a correction factor. If you had integrated the turbulent part from 0 all the way to the end, you wouldn't have got this part or a laminar part, like it would have just been turbulent everywhere. But it's not turbulent everywhere, it's laminar over the first part. So there's like a correction factor to take into account that it's not turbulent over the whole first part. So this ends up with the average Nusselt number is look. So this is times 10 to the 5 to the 1/2. Minus 0.037, 5 times 10 to the 5 to the 4/5 plus 0.037 times Prandtl to the 1/3. So this becomes, this would be correction for the laminar part over the first part of the plate, and it's actually just a constant. So it's a constant, it's negative 871. So it's a correction to the new salt number. The new salt number would be 871 bigger if it were turbulent everywhere. So again, if we want to throw in some actual values for this, this equals negative 871, 0.037 times 7 times 10 to the 5 to the 4/5 times the Prandtl number. I don't think we have that written down, but we can go and look it up. Okay, the Prandtl number is 0.737. (737) to the 1/3. That's 1754. So basically the fact that we had laminar flow over the first part decreased our new salt number by about a factor of 2. So if it was turbulent everywhere, it would have been 1754 for that insight, but it's 1754 minus 871. So this would be, gives us a new salt number of 797, which equals the average convection coefficient times L over K, which equals average convection coefficient 0.4 meters divided by the thermal conductivity of our fluid, which again, if we look it up, is, is 24.3 times 10 to the negative 3. And we can calculate H 48.4 watts per meter squared Kelvin. So one thing I think to just take a note of is if we look back at what we got for air, we got a convection coefficient of about 30. So we're almost 2 times different. The only thing we changed about the system was what gas we're using. We're using the same geometry, the same size, everything, same temperatures. We just changed out the gas. And if we look actually at air and carbon dioxide, they don't have wildly different properties. So like the thermal conductivity, air actually has a little bit better thermal conductivity than carbon dioxide. We would think that would make convection better. It's more conductive. Air actually has a little bit higher, and if we look, so there's the thermal conductivity, 24.3. The thermal diffusivity, how well like heat moves through carbon dioxide is actually worse. 19.5 compared to 38.3. So heat moves through carbon dioxide like half as good. But we get a convection coefficient that's twice as much because we flipped from laminar to turbulent. Just to show how important that is. We have like worse thermal properties. It conducts heat less well, heat moves through it less well. But we get way better convection because of the turbulence. So just to show kind of how important, if you're aiming for heat transfer or aiming for good convection, you have to be aiming for a turbulent flow. And things that you can do, even changes that like in some ways make your system worse. If they give you turbulence where you didn't have it before, it will make your convection better. Because as you change up like what the type of heat transfer is, that's like whether it's laminar flow or turbulent flow, that changes things very significantly. Okay, so back here. Okay, let's do one more iteration of this same example, but without kind of maybe. See if it's working. But without going through all of the kind of extra stuff, just to see like how do we solve an example? Like once we've solved one before, how do we solve a new problem? So let's choose, call this example 3. So and we're going to try to solve this. I'll try to solve this just like how I would actually go and solve it, say for a homework or an exam. So we have same kind of plate. Let's say this is 3 meters by 0.2 meters, so a little bit of change in dimensions. Our velocity is 6 meters per second. T infinity is 25. Surface temperature is still 230. We want to find our properties at this average temp, which is 400 K. So if we look it up, we can find that the kinematic viscosity is 10.6 times 10 to the negative 6 meters squared per second. The thermal conductivity is 134 times 10 to the negative 3. And the Prandtl number is 152. So a lot different than what it was. So step 1 is find the Reynolds number at the end of the plate to see what type of flow is it. It's certainly going to be laminar over the first little bit, but is it going to flip to turbulent? 6 meters per second times 3 meters divided by 10.6 times 10 to the minus 6. This gives us a Reynolds number of 1.7 times 10 to the 6. So this is a large Reynolds number. So this is going to be turbulent flow at the end. It's going to start laminar, flip turbulent. So we have to figure out where that transition takes place. It's going to flip at a Reynolds number of 5 times 10 to the 5. So we can figure out where that's happening, the location. So 5 times 10 to the 5 equals 6 meters per second times x over kinematic viscosity. And our transition happens at about a little less than a meter down the plate. So our model for this flow is the Nusselt number 0.037. This is the exact same model that we used before. This is how it would be written. This is how it's written in our book, where you would look it up. Where A is this correction for the laminar region. Which depends only on the critical Reynolds number. Right, so the A value that we used before, so rate A equals 0.66 664 times the critical Reynolds number to the 1/2 minus 0.037 times the critical Reynolds number to the 4/5. Which If we calculate that for a critical Reynolds number of 5 times 10 to the 5, A is 871. So that's what we used before. So the new salt number is equal to 0.037 times our Reynolds number, which is 1.7 times 10 to the 6. To the 4/5 power minus 871, which is this correction factor, times the Prandtl number to the 1/3 power. Gives a new salt number of 1.44 times 10 to the 4, which equals the average convection coefficient times L over K. L is 3 meters, K 34 times 10 to the minus 3 watts per meter Kelvin. And we can then calculate the convection coefficient, which is 6.4 times 10 to the 2. Or at 640. Yeah.
Why didn't that correction number change? Your like REL, like function of L, and now your L's 3 instead of 0.4.
So the A value is only a function of the, like, here, it's only a function of the critical Reynolds number, which is 5 times 10 to the 5. So it doesn't have anything to do with the length, which is kind of this weird result. So you'll see, you can solve it either way, like either with this equation. This is the correlation that our book will have. I kind of prefer the one that we used up here. Like those are the same models. One just explicitly tells you a little bit more about what's going on. The other one kind of throws that and says, well, we'll throw it into a constant. Our book will throw it into that constant A if you like are looking through and finding equations. So I wanted to at least point out that's what they're doing. But you can see, like if you can identify the right model, the process actually isn't that hard. And this is going to be true for other, like we're going to take the same idea and extend it to other systems. Before we do that though, that won't take us that long because it's all basically the same stuff. It's useful to ask, how accurate is this? So you can get with these types of models, your accuracy is going to depend a lot on the specific system. So sometimes your model might be spot on. Sometimes you can have some fairly large errors. Maybe errors as large as like 10, 20, 25%. So be a little careful when you're calculating this, like, don't show a number to 5 significant figures, for example, because there's simply a lot of error in these types of models. There's a lot of stuff happening with convection. Um, One of the sources is really for all of these fluids, the properties are going to be temperature dependent. So we're typically going to be neglecting some of those changes. The models are going to be neglecting some of those changes that can throw things off fairly significantly. You can have surface roughness. So surface roughness will affect like how turbulent the flow is, or it can make it flip to turbulent earlier on, which can have a fairly large effect. Or if it's a really smooth surface, maybe it stays laminar for longer. And we saw earlier how big of a difference even like a little bit of turbulent flow can have on a system. So exactly where that transition occurs can have a big effect. Surface roughness is one part. So is fluctuations in the free stream velocity. So if it's six meters per second on average, but it's varying a lot, or there are some turbulence in that free stream that can cause turbulence to happen earlier, which can give you pretty different results. Kind of in the same vein, if you do have turbulence in that free stream, that's obviously going to have a big effect. So the biggest effect in a lot of cases is things that are going to give you turbulence earlier or later than you expected, because that has a huge effect. Okay, so so what if instead of flat plates, what if we change geometry? What if instead of a flat plate, we have a cylinder? So for all of these problems, kind of similar to what we did with a flat plate, we're going to have different models and different flow regimes. So when our flow changes, like laminar to turbulent, our model has to change with it. The same kind of thing is going to happen with flow over a cylinder. So in super low Reynolds number, then our flow is going to come in and look like this. So we form like a nice, everything will stay laminar, we'll form a nice laminar boundary layer. But even with cylinders, even if the flow gets a little bit faster, we end up our flow is going over, but then we end up forming a wake behind our cylinder. So we can look a second at what this wake looks like. Okay, so this is a cylinder in cross flow. And with a lot of these, you're trying to look at like what's the fluid doing, and then how can we use that to translate into our model. This is a cylinder. We're going to be releasing smoke at the poles at the top and bottom of the cylinder. So you'll be able to visualize what's happening. So you can see this is super, super slow, super low velocities, and we still have a wake happening behind the cylinder where we have these vortexes form. So this wake becomes really important. So we're going to have, again, the same kind of thing. There's typically in these things, there's going to be a wake behind them where they're creating turbulence. Our models, though, are going to be a lot the same. So we still expect our general model for the Nusselt number to be equal to C times the Reynolds number to a power times the Prandtl number to a power. We just have to find, in different flow regimes, all of those things will be different. Okay, so we typically get kind of two separate parts of the boundary layer with cylinder and cross flow. You end up getting this boundary layer, what we call boundary layer separation. That's what's causing the wake behind the object. We're not going to go too much into this. If you want to know more about it, take fluids class or be in fluids class right now. But basically what happens is as you go to the top of the cylinder, this point here is your lowest pressure. And then as you go over the top, pressure is starting to go up, which going from low pressure to high pressure, things want to slow down. So that like you end up having low pressure pushing on one side and higher pressure pushing on the other side, which can stop your flow and cause it to flip in the other direction and causing some of this, the wake that you guys saw. This wake, again, is a function of Reynolds number. So different Reynolds numbers, that wake might look very different. So we're going to have different models for different kind of regions where, okay, it looks this way here, so we'll use this model. It looks this way here, so we'll use this model. So figuring out there's not going to be a single model that captures all of this. You're going to have multiple models that like kind of work well in different areas or at different Reynolds numbers. Okay, so we can see some of that play out. So this is our general model for a cylinder and crossflow. So we're going to have essentially the same basic form, where the Nusselt number is equal to C times the Reynolds number to a power Prandtl number. We actually still have Prandtl to the 1/3. But the Reynolds number is to a different power because we have different regions where the flow looks different. So we can get kind of correlations like this, where at super low Reynolds number, this is what things are looking like. When we change the Reynolds, we go up a little bit faster, then the flow changes, so we have to use a different correlation. We change the speed, okay, now the flow changes again, we have to use a different correlation. So it's the same basic idea, but you're trying to make sure your model only ever works like when the flow looks a certain way. And once it looks different, then you have to use a different model. So we get models that are kind of tailored for specific subsets of the Reynolds number. But, okay, so we'll do an example and we'll talk a little bit more about how geometry can apply to different geometries. But we're going to use essentially all external flow, like we're going to use the same basic framework. Then we'll talk next class about, okay, what do we do if we have flow inside of an object instead of outside? And we're going to, again, use the same basic ideas. How do we find the Nusselt? Well, what are the things that are important? And we'll build a correlation kind of based off of what we know about the physics that's happening. So we'll end there for today. I think you should have enough stuff to handle the homework. And just, I guess, start thinking about the exam that's coming up as well. So hope you guys have a good weekend.